Okay, let's take a look at reaction rates. That's how fast a reaction goes. It can be explosively fast, or it can be extremely slow. We can define it as the change in concentration of a reactant or a product over time. But if you think about it, you can also have a reaction rate that's at a specific time, or at time equals 0, or that accounts for acceleration and deceleration, right? Which this would not be if it's just the average over time. But this one, if it's just over a period of time, we call that the average rate. We can say the rate is equal to the change in the concentration of A, the A being any of the reactants or products in the reaction, over a change in time. So the units will be, since that's square brackets, that's moles per liter for that, and let's say that's seconds, for example, for time, so the overall units here would be moles per liter per second. A limitation of a method like this is that it doesn't tell you how fast the reaction is when it's beginning. It ignores things like acceleration and deceleration. That's the problem with taking an average. And it can't indicate the rate at a given point because it's over time. So as you might imagine, there's other ways you can measure the reaction rate as well besides just the average rate. You can measure the initial rate, how fast it is when it starts. You can measure the rate at any given point in time. That's called the instantaneous rate. Or you can just measure the entire thing by taking lots and lots of points and generating a curve. That's called the integrated rate. So all those are useful depending on what you want to do with them. And here's a graph that shows several different types. The reaction is the decomposition of nitrogen dioxide. The red is the oxygen. And the initial reaction would be the initial slope here. So for example, there it is, right? This initial slope right there, where it's tangential at time equals 0, is the initial rate. In this case, for the decomposition of nitrogen dioxide, that's that curve. There we are, right there. Position 2 would be the instantaneous rate. We're referring to that line right there. That hits the curve for nitrogen monoxide formation at about 200 seconds. So it would be the instantaneous rate at that given point for the formation of that. And position 3 is covering a period of time, and you're just taking the average. That would be the slope right there. And that would be the average rate of decomposition of nitrogen dioxide in moles per liter per second. If you want to take the most information, you generate the entire curve, and that's the entire graph, which gives you the integrated rate. Notice that this is not like driving a car where you're going 60 miles an hour. You have to think about what you're referring to, and you have to think about what type of rate you are generating, average, instantaneous, etc. Here it is presented in a different scheme. There's an average rate. There's a initial rate, which is instantaneous since it's tangential at time equals 0. There is a instantaneous rate at right about that time right there. And if you wanted to generate this whole curve over this point, that would be an integrated rate. So all of them have their uses. Which formula should we use? Well, the average rate you can use without using something called rate law, and I'm going to skip it. I'm not going to talk about rate law because it's just going to bog us down. So there's the average rate we've covered before. The initial rate would be equal to some constant times the concentration of A to a power. Bear with me for that if that seems weird. It'll become clearer over the next few slides. The instantaneous rate at time equals 0 is the initial rate. At any other time, it would be an instantaneous rate. I don't think you'd call it integrated. This should say instantaneous. I'm going to fix that. And over a period of time, generating the entire curve, that's an integrated rate. Okay, that's an introduction to rates of reaction, also known as kinetics.